Bienvenidos, Hushamadid, and welcome UMGC learners for the CMIT-455 Section 6380 course, which is the Cisco Networking Academy CCNP ENCOR version 8 curriculum for the spring 2021 semester. In this packet tracer activity and tutorial, we're going to be taking a deep dive look at packet tracer activity 8.2.1, where we will be configuring OSPFv2 in a single area. And we're going to be talking about a number of OSPF configuration commands and configuration settings that we should be taking into consideration when we configure the open shortest path first dynamic routing protocol. So let's go ahead and dive in here. Here's the activity. We have our addressing table here at the top. Our objectives are to configure OSPFv2 routing, and then we're going to perform some basic verification. Now, as you can see, this activity is not calling for a lot of configuration tasks to be completed. Now, certainly we have to go to router 1, router 2, and router 3 to make those changes. But again, this is not a lot of configuration, and this is going to ease us into some more advanced configurations, working our way to multi-area OSPF. And so here we're going to have a single area. Now, one of the first questions I get asked about the backbone area by learners is whether or not the backbone area, area 0, has to be the area that's configured if you're only going to have one area. Now, technically, the answer to that question is no. And I've gone into customer environments where I've seen that they've decided to, sort of tongue-in-cheek configure area 51 as the only area that they have configured. Now, that is going to limit the ability of that network from an OSPF area perspective to scale if they think they're not going to use area 0 for the second area that they would configure. So it's always a good idea and a best practice to configure area 0, which is referred to as the backbone area, as the area that you're going to be using. And so let's dive in here. And it just basically wants us to configure the following settings on each of these routers. So on router 1, we'll go from user exec to privilege exec with the enable command, and then into global config. Now, the first thing I'm going to check for is I'm going to check to see in our configuration, do they have any kind of a OSPF config that might be there partially configured? And we don't, and so that's good. So we're going to basically say router OSPF, and then we're going to be entering in the process ID. Now, you can see there the available process ID value numbers. And what I'm going to tell you right now is OSPF specific. The process ID numbers do not need to match for an adjacency to come up and be configured. And so on router 1, I could use process ID 1. On router 2, I could use process ID 2. On router 3, I could use process ID 99. The process ID number does not even have to match the router number. And so you can use any value that you want. However, just like you could change the sub-interface number when creating sub-interfaces so that they don't match the VLAN number for which that sub-interface is providing service, you would be crazy not to do that, right? Don't make it more difficult on yourself and, more importantly, on those who might follow in your footsteps to support the environment that you've configured. So again, we're standardizing here on process ID 10, right? So router OSPF 10. Now, the first thing we're going to configure is the router ID, and I want you to think of the router ID as the fingerprint for this router in the OSPF domain here that we have. Now, it needs to be unique because OSPF as a link state routing protocol, and more specifically, as a link state routing protocol that is based on Dijkstra's shortest path first algorithm, which is really a graph underneath all of the sort of high-level commands that we run. It is a shortest path first tree that gets built. It's a graph of my shortest path to reach some destination. When I say my, I'm talking right now from the perspective of router 1. And so we have to be uniquely identified in this graph so that there's no ambiguity, there's no confusion, there's no duplicity in the fact that maybe someone else has the same router ID that I might have. Again, me being router 1. So the router ID needs to be unique. And if it is not unique, an adjacency, a full adjacency, will not be formed between the two routers. And so the command to do this is simply router ID, and for router 1, it's going to be 1.1.1.1. Now, that said, a convention that I like more than the first, second, third, and fourth octet reflecting the router number is this convention here. And you'll see why shortly. And we'll talk a little bit about how the router ID is actually selected, right? And so the first priority is if it is manually configured. If I manually configure the router ID like I just did, that is the router ID value. Full stop, right? If I don't configure the router ID value manually like I just did, what's going to happen is when I start the OSPF routing process, the router is going to then look to see, do I have any loopback interfaces configured? And if I have a loopback interface configured, that value would be the value that I would use for my router ID. Now, 1.1.1.1, and then, excuse me, and then a loopback address, those look very, very similar to an IP address. And that may cause confusion when you're looking at specific OSPF commands like show IP OSPF database. And you're looking, and we'll see that here shortly. And when you're looking at that output, it could become unclear or confusing as to which router you are actually looking at. A naming convention like this, if it can be used in your environment with the 0001 and 2, and again, we have up to 255, which is probably going to be more routers than you have in your environment, that convention cannot be mistaken for an IP address, right? If you look at 0.0.0.1, you're not going to be thinking, oh, that could be the serial 000 interface IP address. It simply doesn't look like that, right? Doesn't look like an IP. Now, the router ID value takes the form of of a 32-bit dotted decimal value that looks like an IP address, but the router ID is not an IP address. In other words, when I'm done with this configuration, you're going to see that I can't ping the router ID. That is not what the value is being used for. It's not to provide reachability to the router from an IP perspective, right? Ping, SSH. I can't SSH to 1111 because it's not configured on router 1 as an IP. It's configured as the OSPF router ID value. And so again, the router ID needs to be unique among all of the routers in the area, right? And I'm referring to this is all going to be area 0, and so that is my routing domain. When we get into other scenarios with multi-area OSPF, we'll talk more about the router ID value and the importance that it takes. Now, there is I don't want to say it's a corner case, but if you were doing MPLS Layer 3 VPNs, something that we'll be talking about at some point in this course, This router OSPF process ID, and so I'm transitioning back to the process ID here just briefly. That process ID value does play a part when provider edge and customer edge routing protocols come into play. So keep that in mind for the process ID. Again, way outside the scope of this activity, but it is going to come up in the course. So back to the router ID. If it's manually configured, that is going to be the router ID value. If the router ID, excuse me, if the router ID is not configured with that command, then it's going to take the highest IP address, the highest, and you usually hear highest numbered, but it's talking about the IP, not the loopback number, because you could say interface loopback 99, interface loopback 200. That's not the highest number it's talking about. It's talking about the IP address, where 192.168.1.20 is going to be higher than 10.0.0.5. That's what it's talking about. And if that loopback interface is not shut down, and it shouldn't be, by definition, loopback interfaces are always up unless you manually shut them down, then what you're going to have is the router ID is going to be the highest numeric IP address on a loopback interface. Now, if you don't have any loopback interfaces, then it's simply going to take the highest IP, right, the highest numeric IP from any up interface, from some other interface that's configured on the router. If you have no interfaces configured, if there are no interfaces, loopback or otherwise, and you do not have the manual configuration for the router ID, then you're going to get an error message when you try to type in router OSPF and the process ID number. All right, so that's your router ID selection criteria. Again, as I'm spending a little bit more time on this because this is a critical component when you're configuring OSPF, and it's that router ID value. All right, so it says a network address for each interface. Well, let's go ahead and say do show IP interface brief. And we can see we have the two serial interfaces here, 000 and 001. And let's say do show run, and let's find out what those look like. So they're both /30s, which would be a dotted decimal subnet mask notation of 255, 255, 255, 252, meaning the first 30 bits are network bits, leaving the remaining 2 bits to be your host bits. And so that would mean we would have 2 raised to the second power minus 2 usable assignable IPs available, and meaning we have 2 IPs that we can assign in that subnet mask range. Okay, so now it wants network statements. So we're going to say network 172.16.3, and now remember, if there's only 2 possible usable addresses in a /30, if this is .1, then the network ID would be 30.0. Now, this comes up often. Sometimes you will see the following, and this is actually what you should see, and this is a Cisco best practice. And having sat for the CCIE lab exam twice, once in San Jose and once in Raleigh, North Carolina, this is a best practice, is to go ahead and put in the exact IP address of the interface, followed by a quad 0 wildcard mask, right? Now, remember, everything that we're configuring here is going to be in area 0. However, let's see if they're looking for the network ID followed by the wildcard mask for a /30 and then area 0. And that is exactly what they're looking for, because that was 10 percentage points right there. And so now to rerun the command, I can just hit the up arrow and we can make the change here to the 192.168.10. Now I say dot and I stop because it's a /30, meaning that there are only 2 usable IPs. And if I'm using .5 here, and the first subnet in this range would be with a network ID of 0, so it would be 0, 1 and 2 are the usables, and then 3 is the broadcast address. The next subnet would be .4 for the subnet ID, 5 and 6 are the usable, and 7 is the wildcard. Not the wildcard, the broadcast address. And so it would look like this. We would put in the network ID, not the address of the interface, unless we had quad zeros as the wildcard mask in this scenario. And I put that in, and again, we get another 10 points for that. All right, so the LAN interface set to passive. Do not use the default keyword. Now, this is what they're referring to here. I could say, I'm sorry, not default information originate, passive interface, default, right? And so this is one approach that you can take to ensuring that the LAN-facing interface, and let's pull out ink to go here. So I'm on router 1 right now, and it's asking me to apply this passive interface command to that LAN-facing interface. Now, the reason that you would passive this interface is to prevent that interface from sending, multicasting out OSPF hello packets. And the reason that we don't want that to happen is because there are no other routers out here on this LAN segment with whom router 1 would attempt to form an OSPF adjacency. And in these OSPF hello packets that are used to discover and establish and then maintain OSPF adjacencies with other routers, there is a lot of very valuable information from a network perspective that a bad actor could use against you. And so let's take a quick pause here and let's look at what that information might entail. So here I am in Wireshark, and I'll actually clear the drawing off. Here I am in Wireshark, and I'm going to start a Wireshark packet capture. And we're going to go on to router 8 and router 9. And so we'll start with router 8 here. So if I was to go into global config and say router OSPF 10, and then say network 10.0.0.8, area 0. Now, this is the fast Ethernet 00.10 interface on this router. So it's a sub interface, but I can run a dynamic routing protocol on a sub interface basis. And as soon as I hit enter, this is an up interface here. Let me go ahead and say do show debug IP. And let me get back down here. I'm going to make sure I get the right command here. So I need the context sensitive help. So we're going to say debug IP OSPF. I believe it's packet, and we want IP OSPF hellos. And there they are, hellos. Okay. So I'm debugging the hello packets right now, because what we should see here is every 10 seconds, and here's my timer, and it's going to be approximately every 10 seconds. It's not going to be exactly .638, and you can see right there, we're off a little bit. This is the millisecond timer here after this period. But you can see we're just about 10 seconds. We have an OSPF hello packet that is being multicasted out to the 224.0.0.5 multicast IPv4 multicast address. And this is the all OSPF routers address. In other words, what's happening right now is router 8 is multicasting this packet out to any other OSPF listening router who's listening for these multicasted packets. Because if that router's listening, that means, hey, I speak OSPF, and maybe we can form an OSPF adjacency. And this is how the OSPF discovery process works. Now, we're not seeing a ton of detail in here other than the fact that every 10 seconds, as soon as I enable the OSPF process on that interface, it is now trying to discover and acquire other routers who would be interested in speaking OSPF. So this is where, I think I might have said Packet Tracer, where Wireshark comes into, has a lot of value here. And you can see right here, let me drop this down a skosh. So there's our OSPF hello packet. Let me stop the capture because we've got the packet we're interested in. And here it is. And Wireshark is going to allow me to go deep dive into this hello packet to see what exactly is the information that this router is sending in this OSPF hello packet. And so you can see here, and this is where we'll see, excuse me, that OSPF is using IP protocol number 89. Right? It's using protocol number 89, which is different from EIGRP, which uses 88. And so what do we see here? Our source address. Well, that gives the interface address of the router away right out of the gate. So if I'm a bad actor and I'm sniffing the wire and I get this packet, okay, that means I must be able to see this 10.0.0.8. That's going to be the interface IP of the router. There again is the all OSPF routers multicast address of 224.0.0.5 out to which this packet is being multicasted. So now let's get into the OSPF hello packet itself. You can see right here, Wireshark tells us that this is an OSPF packet. Let's take a look at the header information. Well, here we can see the message type. The hello packet is type 1 is a hello packet. You can see the router ID, and there is the loopback address of router 8. It's 8.8.8.8. If I was to come over here and say, show IP interface brief, and again, we've got a few addresses here, but when we get down to loopback 0, excuse me, we can see that it's 8888. And that is how the router ID was selected. Now here is, and again, this is the header information in the packet. Here is the hello packet. So now I've got the net mask value. We can see the hello interval is every 10 seconds. If there were options, they would be listed here. We can see that the router priority, and we'll talk about the router priority as we start to talk about DR and BDR, or designated router and backup designated router selection. You can see the dead interval is 4 times the hello interval. By default, for broadcast network segments in OSPF, the hello is going to be every 10 seconds. The dead interval is going to be 4 times that, or 40 seconds. Again, I see the designated router IP address, which is this router. And so I've collected up some pretty nice information here about, and again, we've got extended type length values, excuse me, not of interest to us right now. But you can see that I get some pretty interesting information. Now, if I'm sniffing the wire and I'm getting this information, I can now, if I wanted to, go ahead and configure myself, if I'm a bad actor and I've got some sort of a malicious program that mimics OSPF. I know the subnet mask that's being used. I know the IP address of who I would want to be my neighbor, and then I could go ahead, configure my program to run OSPF, and then inject bogus routing information into the OSPF routing domain. And if you're asking, well, wait a second, there has to be a way to stop that, you're right, and there is. And what we can do is we can set up authentication between the routers. Again, something that we will be getting to, but that's not covered here in this activity. And so that is why we would want to passive the interfaces that face LAN networks, right? In other words, you passive the interfaces that are facing network segments where there are no other OSPF speakers. Now, we do not passive the serial interfaces because not only do I need the hello packets to go out these serial interfaces to discover and acquire and then maintain the neighbor adjacency with router 2 and router 3, right? We have to have that for OSPF to function. But to send those hello packets out to a LAN segment where there are no OSPF speakers does not make any sense. And so the way that we stop the hello packets from being sent is to say passive interface. If I say default, which it's telling me not to do, if I say default, the result will be that all interfaces on this router will be passive OSPF interfaces, which is not what we want. We simply want, and I think it's gig 00, we want a passive gig 00. That is the only interface that we want to passive. Now, it stops the sending of hello packets out that interface, but it does not prevent the advertisement of the network on the interface, which we enabled the OSPF process on, or we're getting ready to here in a second. It still advertises it out to other OSPF speaking routers. So don't think that when I say passive interface, that it turns OSPF off completely on that interface, right? It stops the sending of hello packets, but in terms of an advertisement with that network, 172.16.1.0/24, that is still going to be advertised. That is why we add a network statement for the 172.16.1.0/24, which would be a 0.0.0.255 wildcard mask. With the network statements, we use the wildcard mask. Remember, when we looked at static routes in the previous video, we were using subnet mask values. With the dynamic routing protocols, specifically OSPF, EIGRP, we're interested in the wildcard mask when we're using network statements. Are there other ways to configure OSPF on interfaces? The answer is yes. We'll definitely be talking about that as we move on here. And I'm going to say area 0. Again, it's in the same area. Everybody's in area 0. So as soon as I entered that command and hit return, router 1 is not sending OSPF hello packets out the gig 00 interface because we have said make that interface passive. But passive does not prevent this network from being advertised to my other OSPF speaking routers in my OSPF routing domain. So that should do it. Excuse me. Sorry about that. That should do it for, and I'm just reading here real quickly, for that setup. Okay, so now we can move through these other routers with a little more speed. And so here I am on router 2. We'll go to privilege exec into global config, router OSPF 10. The first thing I'm going to do is set the router ID to all 2s. I'm going to passive what I believe to be, and I should probably double check this, do show IP interface brief. And let's see the interfaces that we have here. And it is gigabit Ethernet 00. So passive interface gigabit Ethernet 00. And then I'm going to add my network statements in here. So I'm going to say network 172.16.2.0. And we can see from the diagram above, it's a /24. And it's going to be in area 0. And then we're going to do the serial interfaces, which are going to be network 172.16.3.0.0.0.3, and I'm just reading these values here to make sure I'm getting the IPs correct. Now, as soon as I enter this command, what we should see is an adjacency form, a full adjacency form between router 1 and router 2. And again, it could take a couple seconds, and it always depends kind of on how busy the network is, things like that. Excuse me, timing of the packets. However, you can see we've gone from loading to full. And so again, the hello packets have been sent out. And then once the routers discover each other, you have database description packets. They're sometimes referred to as DD or DBD for database description packets. And then you would have link state requests. And these are the OSPF messages that are going back and forth, right? And a link state request is going to say, well, hey, I'd like to know a little bit more about the details of your link state database. Remember, OSPF is a link state routing protocol. And then if you were to have updates, like we're about to have here in a few seconds, as soon as I say network 192.168.10, excuse me, .8, 0.0.0.3, area 0, right? I have just enabled the OSPF process on the serial interface serial 001 on router 2. Well, this would be an update because right now, router 1, what do I see? Show IP route OSPF. And this is the show IP route command. And what I'm saying is, show me only the OSPF learned routes in the routing table. I don't want to see all of these other, local directly connected. I don't need to see that. Show me what I'm learning from the OSPF routing protocol. Now that I have an adjacency with router 2, and router 2 is advertising this LAN segment right here to me. And this proves that just because I use the passive interface command, it doesn't prevent the advertisement of this network. It simply stops the hello packets from being sent out that gig00 LAN interface. And so as soon as I hit enter here, we're going to have a link state update of some kind, right? Because router 2's link state database is going to change, and there's going to be an update that goes out with this new information. I'll hit enter. We're going to see an update that would go out, and then here on router 1, we see that our link state database is now synchronized because we now see this advertisement for that transit segment, right? This is referred to as a transit segment between routers because it's across this segment that traffic is transiting, right? So we refer to that as a transit segment. And then there would have been a link state acknowledgement of some kind, referred to as an LSAC, right? Or LSAC, sometimes I hear, but it's LSAC, right? That confirms the receipt of a link state update message. So we've got our adjacency here. Now I can also say show IP OSPF neighbor. Probably one of the first commands that you should run if you come into an environment where you believe OSPF is running and you're looking at the routers. This is going to show me a number of important things. You can see right here, neighbor ID. That is not, now see, this is the challenge here. It looks like a loopback address, doesn't it? Because we could configure loopback addresses for these routers that are 2222 and 1111 respectively for router 2 and router 1, or router 1 and router 2, however you want to look at it. I could make that a loopback address. And that's the router ID. Now imagine you don't have any loopback addresses and it simply grabbed the highest numbered IP off of a physical interface, and that interface would have to be up when it grabbed it, right? It grabs that value, and it's just some value that you can't really immediately associate to that router. That could be confusing, right? And so it's always good to try to come up with a unique, very recognizable, conspicuous router ID numbering convention, configuration convention. And I like the 0.0.0. Some value, because when you see that, you know right away that that is not an IP address that I'm using in my routing domain. So that is the router ID of the neighbor. That's what neighbor ID stands for here. It stands for router ID. That's my neighbor. And again, it's the fingerprint. It's the identification. If you're in the States, it's the social security number of router 2 that I'm seeing here. Now, this value is important because from a testing perspective, Cisco loves to ask you questions like this, right? Why is that value 0? And the reason that that value is 0, or the question might even say, on this segment between these two OSPF speaking routers here, which one is going to be elected as the DR and which one's going to be the BDR? And they show you an IP address for router 1 and they show you the IP for router 2 on this segment. And they try to bait you into thinking, oh, it's got to be the highest numbered IP. Well, this is a point-to-point network type. It's a serial point-to-point network type. How could I see that? What if I said show IP OSPF interface? Now, unfortunately, and I'm going to tell you this before I even hit the question mark, there's an option here for brief, which is really, really nice Unfortunately, Packet Tracer does not have that option. So we're going to get the whole enchilada here. What that command with the brief option, would look like, and let's turn off the debugs here and say you all. And that turns off all debugging that you might have going because I don't want it to continue to show me the hello messages here. So you all stands for undebug all. All right. So show IP OSPF interface brief, right? And that's the option that I'm using is interface brief. And you can see this gives me a nice little consolidated list of output. Now take a look here at the state. It's listed as the designated router. Process ID is 10, area 0. We've got the address and the mask. How many neighbors do I have that are either full, right? You can see I've got no neighbors. And again, that's because we haven't configured anybody else on this broadcast multi-access segment to be an OSPF speaker. Now, with the interface option, you can see similar, a lot going on here, right? On the regular iOS, but I can actually put in just the fast Ethernet interface I'm interested in. Okay, if I don't want to see all of this, right? And if you've got 10 or 15 interfaces, you're not going to want to see all of that. You're going to want to see fast Ethernet, 00.10. And again, that's the only interface we have configured on the router, so it looks the same whether I specify the interface or I don't. But on interfaces where you've got multiple links that are OSPF capable links and that you've got adjacencies over, you're going to want to specify the specific interface. And so what do we see here? Well, what network type is this, right? When we look at this, you can see right up here, network type is broadcast. So OSPF treats this Ethernet interface as a broadcast network type. And that is what is driving the hello interval and the dead interval of 10 and 40. Remember, the dead interval being 4 times the hello interval by default, right? On a broadcast network type. Now, you can see that the state is DR. It's the designated router. We'll get to that soon. And then we've got the priority value. And the priority is inextricably linked on this interface to the DR-BDR election process and which router for this segment I want to be, either the designated router or the backup designated router. Now, these terms might be confusing, and I will explain why you have a DR and a BDR. But I want you to notice the difference between a broadcast network type with a DR and a point-to-point network type that does not have a DR or a BDR. Where in here does it show me the DR? Where do you see that? You don't. On a point-to-point network type, when I say show IP OSPF neighbor over a serial interface, right here you should see DR. But you see the dash and you see the priority of 0. Remember, I told you that the interface OSPF priority value is inextricably linked to the election process that takes place for the DR and the BDR. The priority values range from 0 to 255. If it's set to 0, that means I don't want to participate in the DR-BDR election process. And therefore, you will simply see a dash right here. And this is the default priority value for a point-to-point OSPF network type interface. And you will simply see the dash because we're saying I don't want to participate in the DR-BDR election process. Now, you might be wondering what the difference is. Why, on a point-to-point link, do I not care about whether we have a DR or a BDR as opposed to a broadcast multi-access? And when I say multi-access, I mean an Ethernet segment, a VLAN, where I could have 50 routers that are all speaking OSPF. Now, that's where we're going to launch this conversation. So, the DR, BDR, designated router, backup designated router. Why don't we have them on point-to-point serial interfaces? Whoops, and that is a terrible serial. I apologize. I'm using my mouse to draw right now. So why do we not have the DR, BDR, and I'll just put an X through it, but if I have a broadcast network type where this is a switch and we've got a router here, maybe I've got a router over here, I've got another router over here, there's a router over here, another router over here, and all 5 of these routers, and let's say they're all in the same VLAN here on this switch, they are running OSPF, and we do have a DR, BDR election. And here's why. Let me ask you, and I'm going to walk you into the answer, and you're going to discover this answer on your own. How many routers can I have on either end of this point-to-point link? This direct connection between these 2 routers. What's the total number of routers that could participate in OSPF on this point-to-point link? And I'm not saying we're carving up into sub-interfaces or anything like that, or it's a multi-point. This is a point-to-point network type in OSPF. And physically, how many routers can participate in OSPF on this point-to-point link? And the answer is 2. And so if from router 1's perspective, over this link, I only establish 1 OSPF adjacency, then that's pretty easy for me to keep track of in terms of hello messages and link state acknowledgements and link state updates and all of the other types of packets, OSPF packets that are going to be moving across that transit segment. That is a very different proposition on a broadcast and multi-access, right? Because take a look at this. A week later, I could put a new router in here. 2 weeks later, put another router in here. And so now we end up in a scenario where if I enable OSPF on all of these router interfaces, because, maybe they've got network segments behind them, right? And we need those network segments to communicate with each other. If I enable OSPF on all of these broadcast OSPF network type interfaces, and let's assume that we don't have a DR BDR, how many full adjacencies will I end up with? Well, if that's router 1, it's going to have a full adjacency with router 2, 3, 4, 5, 6, and 7. And then router 2 is going to have full adjacencies with everybody else. And router 3 is going to have a full adjacency with everybody else. And as you can see, just from a messaging standpoint and a traffic standpoint, that's a lot of full adjacencies for these routers to maintain amongst each other. And then imagine a network segment goes down. And then all of these OSPF link state databases on all of these routers have to fully synchronize, right? And that's a very important takeaway. All the routers in an OSPF domain, and we're talking specifically an area here. Our domain right now is just area 0. Within an area, which is our routing domain right now, all routers that are participating must keep the link state database fully synchronized between all the routers, because it's that link state database that details the entire network environment. And so this does not scale. And in fact, John Moy, who is the creator of OSPF, and this is probably a good segue here to this web browser. And I'm going to leave the drawing up here for a second because we're going to go back to the drawing. OSPF, and you can see right here, John Moy, he is the author, the creator of the OSPF routing protocol. He is the author of the request for comment, and this is an internet standard RFC 2328. And again, I really see my role as an instructor as less of an instructor telling you to do things and more as a guide. If you want to master OSPF, this is a great place to start. RFC 2328. And again, OSPF version 2. There's other RFCs for IPv6, which is OSPFv2, and we'll talk about those as well in turn. However, this is a great place to start because this is the standard specification for OSPF. Now, vendors like Cisco or vendors like Juniper or Huawei or HP, whomever else is out there selling routers that are running OSPF, what happens is they take the standard and they create an implementation for their devices that are based on the standard. Now, do vendors deviate from the standard? Absolutely. And Cisco is one of those vendors that has deviated a little bit, specifically in one of the network types, which we will be talking about, which I believe is point-to-point, point-to-multi-point non-broadcast, I think is what it is. I'll have to look that up. But there's deviations between vendors, but this is the place to start. And again, you might think that, well, this is going to be dry reading here, and no. If you are interested in understanding the internals and the ins and outs of OSPF and how it's designed, the RFCs are a great place to start. Now, the next, and again, this is primary source material. And let me take a step back here. There is no better reference material than primary source material. And primary source material is material that is produced by the source producing the technology. That is John T. Moy. He is the creator of this routing protocol. There is no one more familiar with OSPF than John T. And again, I say that, I'm sure that a lot of people know a lot about OSPF, but again, he is a primary source because he is the architect of OSPF. Who better to learn from than John T. Moy? And so that's going to take me to my next reference for you, and that is John T. Moy wrote a book. And again, this book is a little older, but this book is absolutely amazing. Now, some people will argue that the book is nothing more than the RFC in a book, and that is not the case. I have read this book cover to cover, and I'm here to tell you that it is not the RFC reprinted with this cool blue cover and from the inventor of OSPF, call out right here. That is not what this book is all about. This book goes into the history and the reasons why John T. Moy was making the decisions that he was making as he designed OSPF. And as you can see, there's 40 copies right here, and you can pick them up for as cheap as $2 plus shipping. In fact, some of these are offering free shipping. So if you're going to be a network engineer and you're going to be in the networking space, for me, this is a mandatory read in terms of being a network engineer. The RFC is a mandatory read because OSPF is the predominant routing protocol. And let me clarify, because I'm sure someone's out there screaming, no, BGP. OSPF is the predominant routing protocol in terms of interior gateway routing protocols, IGPs, that you would run inside your enterprise environment. I'm not talking about BGP. BGP is its own beast, and it is the king of external communications in terms of routing protocols. But interior gateway protocols, OSPF is the dominant routing protocol that you're going to find because it is an open standard. It is not proprietary, and all of the functionality is out there to be taken advantage of. And now you might be screaming, well, EIGRP, there's an RFC. Well, we'll get into RFC 7868 and exactly what RFC 7868 provides as part of the standard and what RFC 7868 holds back. And you're going to find that it holds back something very, very important in terms of functionality with EIGRP. And so back to the DR BDR conversation, where we were talking about the DR and the BDR. And Moy in the book specifically calls out, and I believe it's mentioned in fact, let's see if it's mentioned in the RFC. I believe it is mentioned in the RFC. And there is a section on the DR. Or let me make it easier here. Designated router. Here we go. So the designated router and the backup designated router. So when you see topics like this and you're reading through its certification, the official certification guide, or other texts, come check out and let's see, hey, what does page 54 say here when it talks about, sorry, come down this way, the designated router, right? And why do we need the designated router? And it talks about it right here, right? The designated router becomes adjacent to all other routers in the network since the link state databases are synchronized across adjacencies. But more importantly, it allows OSPF to scale. So let's come back to the screen here where we have a little less traffic. It allows OSPF to scale from an adjacency perspective. And so here's what I'm going to say. We have that DR BDR election, and router 1 becomes the DR for whatever reason. And router 2 becomes the backup designated router for whatever the reason is. We're just throwing a scenario out here. What this means is all routers will become fully adjacent with the DR and the BDR. So router 3, 4, 5, 6, and 7, they all become fully adjacent with the DR and the BDR. Now, the DR and the BDR are fully adjacent with all of them and each other because, again, we have a designated router, and if it explodes for whatever reason, we have a backup designated router that's fully synchronized. And so then what's the status? Does 7 know about 6? Does 6 know about 5? What about 5 and 4? They don't become fully adjacent with each other. They go to what's called the DR other, and you'll commonly hear this referred to as druther, right? Because it spells DR other spells druther. And they sit in not the fully adjacent state. They will stop in a two-way OSPF state. So instead of seeing full, you'll see two-way. And the reason that it does this is because, one, OSPF needs to scale, and everyone becoming fully adjacent with everyone else is not going to allow that to happen. So two-way state means they know about each other. They know that these routers are out there on this broadcast network type, and they know they're out there, but they're not going to become fully adjacent with them. They're going to become fully adjacent with the DR and the BDR, and it's to the DR and the BDR that they will send all of their LSAs. If we have an update, if a network gets added, if a network goes down, and that's going to go to address 224.0.0.6. And this is the all OSPF DR BDR IPv4 multicast address. So a network goes down here behind router 6. Router 6 is not going to send his notification that this network is no longer in the OSPF routing domain to 7, 5, 4, and 3. That's what we're trying to avoid here, right? It's just this pandemonium of all these link state updates and link state acknowledgements and all these LSA packets flying around everywhere. No. Router 6 is going to send to the 224.0.0.6 IPv4 multicast address the link state update that says, hey, this network's no longer available. It's going to show up at the DR and it's going to show up at the BDR. And then the DR is going to send something out to the 224 0, and you can probably guess because it's got to go to everybody, because everybody needs to know about that, because the link state database for all routers needs to be synchronized. It's going to go out to 224.0.0.5, so that then one person here. So think of it like this. I've heard a great analogy. I can't remember where I heard it. But think of it like this. In this picture that we have here, in this broadcast network type that all these routers are participating in, and everyone sees everybody else. If everybody is sitting and screaming out the same information, it's probably going to be a little bit more difficult to determine who's screaming what, right? If all 7 of these guys are screaming, we got a link state change, we got a link state change. No, it's better if we pick a leader. And then that one person is going to yell out, hey, everybody pay attention. This has just changed in the OSPF routing domain. And that is the way OSPF scales in multi-access broadcast network types, is through the use of a designated router and a backup designated router. And I'll talk a little bit more about the election process as we move on, but let's segue back here and let's definitely clean that up to the activity of which I've been logged out of router 1. So we were on router 2. I think we did everything we needed to do here on router 2, but let's just say show run. I'm going to pipe it to section router OSPF, and yes, that is supported on this version of Packet Tracer. That command right there is going to save you from the show run, either the enter key, or the spacebar. This is how you do it in a real network environment when that's what I want to see. What does my OSPF config look like right now? And it looks like we're done. We're also at 66%, so let's transition over here to router 3, and let's take a look at what we've got here. So if I was to say show run, pipe it to section router OSPF, we don't get anything. There is no OSPF config. We get into global config. We say router OSPF 10. First thing I want to do is set the router ID. And here they're going to keep it simple with the all 3s, matching the router number, not a problem. And then we're going to say passive interface. And before I do that, I need to figure out, it should be gig 00. I see a message there, show IP interface brief, but let's confirm. It is passive interface gigabit Ethernet 00. So we get a few points for that. And now we've got network statements that we need to drop in here. So we'll start with 192.168.1.0, 0.0.0.255, because I can see it's a /24 up there in the diagram, and it's going to be part of area 0. Now, hello packets are not going out that gig 00 interface. It is passive. So we've got the router ID, we've got our first network statement. Now let's get the transit network statements configured. 192.168.10.4.0.0.0.3, because if it was a 252 in the last octet from a subnet perspective, the subnet mask, the wildcard mask is the inverse of that. To get in from the all 255s, we would end up with 3, and that's going to be area 0. We'll see the adjacency pop up here any second now. And now we are fully adjacent with the router on the other side of this point-to-point network type. Again, do show IP OSPF neighbor. Do we have a DR that's being elected? No, because it is a point-to-point network type. The priority is 0 by default on point-to-point network types because you're saying, I don't want to play. I'm not interested in doing the DR, BDR thing. We don't need to do that because it's only you and me, router 3 and router 1. It's just us on this point-to-point link. It'll only ever be just us on this network type in this physical medium that we have here. And then we're going to put the network command in for 192.168.10.8, which is also a /30, 255, 255, 255, 252 is the subnet mask. The wildcard mask is the inverse of that. So instead of 255, 255, 255, 252, we have the inverse, 0, 0, 0, 3. And that's going to be area 0. And now we'll see the adjacency between router 2 and router 3 come up. And there it is. So now let's save our config and let's talk for a few seconds. Again, we got the 100%. Again, You get the 100% completion, that's great. It's more important to have an understanding as to what we just did and what's going on here. So if I say show IP OSPF database, that is what our OSPF database looks like right now. That command is showing me the link state database. This is your link state database. You can see that we've got link IDs. These values right here are the router ID values. Again, when you go in to look at the link state database, you're going to see router ID values in here. And so that's another reason it's very important that those values you choose for the router ID are significant to you and easy to identify. Oh, that's router 1. That's router 2, right? So let's see here if we've got anything else outside. Okay, great, good. So let's take a look. We talk about LSAs or link state advertisements. And there's different types of LSAs. The command that I just ran, and let's see if we can, that's going to force me to do that. So all routers will generate a type 1 LSA. And that type 1 LSA is known as the router LSA. And that's very important to remember because it's in the type 1 LSA where I describe how I see, and when I say I'm on router 3, we're talking about router 3, how router 3 sees the network and the networks to which router 3 is connected. This is how router 3 is describing those things. So take a look here. Connected to another router, point-to-point link. And so if every router generates a type 1 LSA, and in that LSA, it describes the links to which it is connected, and you can see the values that it's providing, this is how the graph with the Dijkstra shortest path first algorithm is going to be calculated. And you'll hear sometimes referred to as a map, right? And that's a great analogy, is OSPF is drawing for itself a map of the network where every router in this OSPF routing domain knows about every other router and knows about every other router's links. Hence a link state routing protocol. And that is what OSPF is all about. And again, I'm not going to go into too great a detail here, but you can see that I have type 1 LSAs, and that's the show IP OSPF database. This is the router link state advertisement for area 0. And you can see router 3 has a type 1 LSA for router 1, for router 3, and for router 2, because it has received those type 1 LSAs. And the information in those type 1 LSAs is information from which the shortest path first algorithm can do its magic behind the scenes and formulate the graph, the shortest path tree for each router to get to each of the networks. And how is that different then if I was to come over here and get onto router 9? And I'll prove to you as well, let's get into global config. I'll say router OSPF, I'm not going to use 10, I'll use 999, right? To show that the process IDs don't have to match for 2 routers in the same routing domain to become fully adjacent with each other. And so then I'll say network 10.0.0.9, because that's the IP address, right? So I'm not doing the network ID, I'm doing the exact IP address here of that router, and we'll say passive interface. And so take a look at that. These are physical Cisco routers, they're 2811s, and now I'm fully adjacent. But I'm fully adjacent over show IP OSPF interface fast Ethernet 00.10. But I'm fully adjacent over what network type? A broadcast network type that has a default cost, right? A priority. I'm sorry, I'm in the wrong spot. I just jumped. Where are we at? Where's there? My priority is right underneath. Has a default priority value of 1 from a DR BDR election perspective. So show IP OSPF neighbor here is going to look different. The priority, which is talking about the OSPF priority, this has nothing to do with the cost of this link or to transit through this link. This is all about the DR-BDR election. And take a look. Router 9 sees router 8 with a priority value of 1. It's fully adjacent. And router 8 is the DR. And you can see right here in that show IP OSPF interface output, it tells you the designated router, who it is. It's router 8. Because router 8 and 9 are both plugged into a switch, just like the drawing I had up earlier. And so if other routers started to join in, we could run into a scenario where we might have some questions about, there's a lot of traffic being generated here, and that's why we have the DR and the BDR. So let's say, from router 8's perspective, router 8 is going to see router 9, show IP OSPF neighbor, I apologize, as the backup designated router. And you can see it right there. So router 8 sees router 9 as the backup designated router. So if router 8 was to explode, and 8 is the DR, show IP OSPF interface fast Ethernet 00.10, excuse me, and you can see designated router ID. I'm on router 8. Hey, that's me. Who's the backup designated router? Well, that's router 9, right? So if router 8 explodes, router 9 in this configuration would become the designated router, right? And that's how that works. If I wanted a router to have more preference to be the designated router, I could go onto the interface, and let's make sure 8 is the DR, 9 is the BDR. So let me come over here to 9. And so let's say that router 8 is really, really old. And believe me, a 2811 is pretty old. If router 8 is really, really old, and we don't want router 8 to be the designated router, because there's going to be a little additional overhead involved there, right, of being the DR. And I want, 00.10. I want router 9 to be the designated router. Well, I can increase the priority. But I'm going to show you something that you might not think is a feature, but it is. And that is if I say IP OSPF priority, IP OSPF priority, you can see the values range from 0 to 255. And this is specifically for the DR-BDR election. On point-to-point links, there is no DR-BDR. You don't need, to change that value. Here, we do if we want router 9 to become the designated router. Now, you might be asking, well, is there another value that gets looked at first? And the answer is yes. It's the higher router ID would become the designated router. But remember what happened. We configured the interface, fast Ethernet 00.10 on router 8 first. And then OSPF sat there and waited for 40 seconds for some other OSPF router to show up. And then they would be able to exchange hello packets and the database description packets and then determine who would be the DR and BDR. But that, we never did router 9, right? We configured router 8 and then went right back to the packet tracer activity. And so there's another value here in this output called the wait timer. And the wait timer is all about the following. If I start the OSPF process up on an interface and I'm sending my hello packets out every 10 seconds, I'm going to wait for 40 seconds to hear from somebody else, or else I'm going to declare myself the designated router, because there's nobody else out there who wants to participate with me. There's nobody who wants to compete with me to become the designated router. So I'm going to become the designated router. But I'm going to wait for 40 seconds. So had we configured router 8, and then within 40 seconds come over here and configured router 9, there would have been a competition based first on the priority value, but that's not set. Those are equal. Then we would have looked at the router ID to see who has the higher router ID. And then that is the router who would have become the designated router. And so here, we're going to go ahead and we're going to set it up so that router 9 would be the DR. But this gets back to something I'd mentioned. You might think this is not a feature. It is. So I'm going to say, I'm going to give it the highest priority value. And I'm going to hit enter. And I'm going to wait a couple seconds. And I'm going to say, okay, no question, router 9 is now the designated router. Well, let's run that show IP OSPF interface command again. Who's the designated router? Router 8's the designated router. Well, wait a second. If I just told you that the higher priority value, and we max that out at 255, router 8 still shows up as the DR. What about show IP OSPF neighbor? Yeah, router 9, I still see router 8 as the DR. And you might be thinking to yourself, okay, it's got to be that 40 seconds. He's got to be waiting for that 40 seconds. No, I'm not waiting for the 40 seconds, right? This is the feature that I'm talking about. And the feature is that you cannot preempt the designated router. And what I mean when I say preempt is I can't just simply go in, put in a higher priority on some other interface that's in this broadcast multi-access segment, and that's going to preempt router 8 and say, no, I'm the DR now. That is not going to be allowed. What would have to happen at this point, and this is why when you go to lay your network out, that's why at this point, what's going to end up happening is we're going to have to reset the OSPF process to force an election of the DR-BDR, because router 8 is going to remain the designated router up until the OSPF process on router 8 gets reset. And so let's do this. Again, keeping with my best practices. So router OSPF 10, do show run section router OSPF. Let's make sure that's where we're at. Yeah, so I'm going to say router ID 0.0.0.8 because I'm not happy that a loopback address that we can get to is reachable. And here's the command that you would need to run in order to reload or reset the OSPF process. This is not reloading the router. However, if you're in a production environment, this is not something you're going to do in the middle of the day, because this would also be a resume generating event, meaning shortly after doing this in your production network, you're going to be looking for a job. So do clear IP OSPF proc, and again, short for process, and I say yes, this resets the OSPF process. Now, you'll notice it went from full to down because we've reset the process, and then the finite state machine for OSPF starts from down and works its way all the way back up, and then finally goes from loading to fully adjacent. Now, do show IP OSPF neighbor. And now, remember, we're on router 8. What does router 8 see router 9 as? The designated router, because it has a higher priority on the interface. Again, can't be preempted, higher OSPF priority on the interface. And remember, the priority has nothing to do with OSPF making routing decisions from a cost perspective. That is not tweaking or manipulating the cost of an OSPF interface inside the graph. That is simply the priority for the DR-BDR election. All right, the final thing I wanted to show you here in this activity that we just did is, can I ping 1111? I'm going to prove to you that while the router ID takes the form of an IP address, being a 32-bit dotted decimal representation that looks just like an IP, it is not an IP. Because look, I can't even get to it. Now, Could I go on to router 1 and create a loopback interface that is 1111 and advertise that into OSPF? Yes, causing even further confusion among the router ID, right? Now, again, if you've got just a couple routers and you use 1111 and 2222, not a big deal, but you want to come up with something a little bit better, especially if you're new to OSPF, that's going to make it a little easier for you to understand what exactly is happening. All right, well, I think that we have hammered this activity into the ground, and we looked at a lot of information here. We looked at OSPFv2, which is implicitly states that that's OSPF for IPv4, and we looked at the configuration in a single area, area 0, the backbone area. If that configuration was going to be the only configuration we had at our company, and I knew it was never ever going to change, could you use an area other than area 0? Sure. You could make it 51, you can make it 99, you can make it 200. It wouldn't matter, but I wouldn't do that. I would always start with the backbone area because I can almost guarantee you at some point it's going to grow, right? We talked about the priority value and that point-to-point network types in OSPF do not participate in the DR-BDR election because they don't need to. But in broadcast multi-access segments, they do. And we talked about why that is. Because we don't want all the routers to be fully adjacent with all the other routers. It's simply going to create too much traffic. And we don't want that. And it goes up exponentially as you add in individual routers if they're going to be fully adjacent with each other. That's what the DR and the BDR are used for. We talked about two great resources. RFC 2328 is a must-read. In the Moy book, for $2, you can't afford not to buy that book. If you want to be a network engineer, you want to work in the layer 3 space, and you want to work with OSPF, those are mandatory resources as far as I'm concerned. All right. I'll get off my soapbox there about the John T. Moy. And no, I have no financial interest in whether John T. Moy sells books or not. Okay, that is going to do it for this video. I hope you have a much better idea about how to configure OSPF, why you configure things in OSPF like passive interfaces, and that this has helped you with your studies. Thank you guys so much for watching, and I will see you in the next video.